There are some properties we can use when we're working with logarithms and solving equations that have logarithms in them. And the first is that given proper conditions on a and b and their sign, the logarithm of the product of a and b is not the product of the logarithms, it's the sum of the logarithms. So the logarithm of a times b is the logarithm of a plus the logarithm of b. Let's take a look at that. You'll recall that when there is no base, it's a base 10. So let's do something that hopefully we understand. A 100 times 1,000 is 100,000. So the left-hand side is the logarithm base 10 of 100,000. And how many powers of 10 do you have to get to 100,000? Well, it's 5 of them. So you can do this on a calculator if you want, but it's going to be 5. But the logarithm base 10 of 100, that's 2, because 10 to the second power is 100. And the logarithm base 10 of 1,000 is 3, because 10 to the third power is 1,000, and 2 plus 3 is 5. And so you can see for these specific numbers, 100 and 1,000 and a base 10, it is true that the logarithm of the product of these two numbers is the same as the sum of the individual logarithms. And this has pretty directly to do with this idea that when you are multiplying quantities that have like bases, what do you do with the exponents? Do you multiply them? And the answer is no. Exponents get added, and logarithms are exponents, and sure enough, they get added. So that's the first property. The second one is very, very much the same. It is that the logarithm of a quotient or a division, it's not the sum of the logarithms, it's not the product of the logarithms, it's not the division of the logarithms. It is the difference. It is what you get when you subtract the logarithms. And when you're subtracting, it's the logarithm of the top minus the logarithm of the bottom. And notice these logarithms could be any base. I've written them as base 10, because when there is no base, it's base 10. But it could be any kind of logarithm, any kind of base. Base 7, base 10, base 11, base e, doesn't matter. So I will quickly run through an example of this. This is 100 divided by 10, that's 10. The log base 10 of 10 is 1. The power you raise 10 to get 10 is 1. Now we have the logarithm of 100. The logarithm base 10 of 100 is 2, because 10 to the second power is 100. Minus the logarithm base 10 of 10 is 1. We discovered that on the other side. And 2 take away 1 is 1, and this checks. Third and kind of final property of logarithms is that I've written this property or this starting quantity with the assumed base 10, but I could put any base in there I want. I'm tempted to put a base like m or n, meaning it could be anything, but then that confuses the issue a little bit with having another variable. So here's the property. It is that when you have the logarithm of something to a power, you can rewrite it as that power times the logarithm of just the something. In other words, this exponent can come down and go in front and be multiplied. And that has to do with, it's not immediately clear why, but it has to do with when you have something to a power like this, you can kind of multiply. It's a little different, but not much different. That's the underlying idea. The next couple ideas are really important, and they probably belong in a later section. But I want to show you what some of these properties can do before I go through and show you some more problems from this section, because those problems from this section are just practice at stuff, and I want you to see what you can do with these. So let's take a real life example. Let's take 3 to the x equals 5. 3 to the first power is 3. 3 to the second power is 9. So x is going to be somewhere between 1 and 2. And we could just guess and try on our calculator. But now we have some properties we could play with. So if these two are equal, then it would make sense that their logarithms base 10 are equal. And we have a property up here that said when you have the logarithm of something to a power, that power can come down in front and be multiplied. And a logarithm base 10 of 3 is just a number. It's some weird decimal, but it's just a number. So we can divide both sides by that number, and we just found out what x is. It's the logarithm base 5 over the logarithm base 3. That is the power that you would raise to. Whatever this number is, that's the power you would raise 3 to get 5. And you could calculate this on a calculator just as easily. And notice when I took the logarithm of both sides, I did the log base 10. But instead, I could have taken the natural log of both sides, and I would have gotten this answer, the natural log of 5 divided by the natural log of 3, and that would give me the same answer. So that's kind of a cool thing. Now, let's use it for something else. What happens if you have the logarithm base 3 of a number like 7, and you can't look up the logarithm base 3 because on the calculator I'm using in Desmos it doesn't have a log base 3. Well, I showed you what you can do. Now I'm going to show you why you can do it. If you want to figure out what this is, you can do the following steps. You could set this equal to x, and then turn this into an exponential equation. This base to this power equals 7. And then you could take, say, the natural log of both sides, or the log base 10 of both sides. The x can come down in front and be multiplied. And then so we now know what x is. We know what this equals. It equals the natural log of 7 over the natural log of 3. So anytime you want to find the log of some base with respect to some base of some number, you can always use this change of base idea. It's the logarithm of this divided by the logarithm of this. And now it's time for a couple examples from this section. This is the logarithm base b of one huge fraction, and the directions say use the properties of logarithms to rewrite this as a logarithm, a series of logarithms where all you can use is the logarithm of w, or the logarithm of x, or the logarithm of y, or the logarithm of z. You can't combine variables, and you can't have more than one of each of those. And so let's get started. We know that this could be written as the logarithm base b of the top minus the logarithm base b of the denominator. That was one of our properties. And we know that with respect to this multiplication, we can break this apart into the logarithm base b of w squared plus the logarithm base b of x minus, and with respect to this multiplication, we could, as long as we have the minus sign in front of the parentheses, we're okay. We could have the logarithm base b of y plus the logarithm base b of z cubed. But we're only supposed to have the logarithm base b of the letters, none of these exponents. And so using the property, we could bring this exponent down in front and multiply it by the log base b of w plus the log base b of x minus, in parentheses, the log base b of y plus, bringing this down and multiplying, the log base b of z. This is a good enough answer. I would accept it. Some teachers would like you to distribute and get rid of the parentheses, and if you did that, you would get this. And so we had one nice compact logarithm of this ugly complicated fraction, and now we've written it as kind of sums and differences of these single logarithm values, logarithms of single things like w, x, y, and z. That's one direction. Now let's look at a problem where we go the other direction. Here we have something written in terms of logarithms of individual variables, and we're going to try to compact it into just one logarithm. And so we're going to kind of reverse the process in the last problem. This 3 that's multiplied in front could come out here. This 1/2 that's multiplied out in front could come here. Then this plus could be written as the logarithm base b of the product of these two things, because we know we can go from the logarithm of a product to the sum of the logarithms. That means we can go from the sum of the logarithms to the logarithm of the product, and now we've gotten this quantity written as just one logarithm. So back and forth, back and forth. It's good practice on the properties, really good practice on the properties. But these problems aren't accomplishing too much. Let's do one last problem in this section. Here we're given some information about a certain base b, that the logarithm base b of 3 is approximately 0.792, and the logarithm base b of the number 5 is about 1.161. The idea here is not to find b. The idea here is to use this information to calculate each of these, and so let's give it a try. Now, it might not be clear to you how 45 is related at all, so let's see here. 45 is 9 times 5, and that's 3 times 3 times 5. So this is the logarithm base b of 3 plus the logarithm base b of 3 plus the logarithm base b of 5, because 45 is 3 times 3 times 5, and then we have a property that says the logarithm of the product is the sum of the logarithms. And this is 0.792, and this is 0.792, and this is 1.161, and you add up these three numbers, and you get the answer. That's the logarithm base b of 45. What about 1/5? Well, what can we do? Well, we have the logarithm base b of 1 minus the logarithm base b of 5. This, we know what it is, we're given. But what about this? What is the power you're going to raise b to get 1? B to some power equals 1, but isn't a number like 7 or 8 or 9 to the 0 power always 1? So this is 0, and I can do that subtraction for you. It's going to be negative 1.161. So these problems, somewhere around problem 59 on page 810, they're just little puzzles. You're given some information, and you try to puzzle together the answers to the problems.